will be Urs Wiedemann, and the title of his talk is Jet Quenching and Quark-Antiquark Dissociation in Heavy Ion Collisions and String Theory.
Okay, good morning. I would like to thank the organizers very much for their kind invitation, and I would like to use this opportunity to discuss some recent developments in the theory of ultra-relativistic heavy ion collisions, developments in which string theory has had an impact. Let me put this into a wider context. The LHC is scheduled for start-up within a year. Machine and detectors are optimized to search for beyond the standard physics models. However, the machine is very versatile. It will also collide heavy ions at 30 times the center of mass energies so far studied at the relativistic heavy ion collider RIC in Brookhaven. So this allows us to test matter at unprecedented high energy densities, and it gives access to a wide range of questions of how collective phenomena and macroscopic properties of matter can emerge from the standard model, Lagrangian. Now, string theory parallels this development to a large extent. On the one hand, it aims at a top-down approach to beyond the standard model physics, and on the other hand, there have been several technical spin-offs in recent years which allow novel calculational techniques to be applied to the study of non-abelian thermal quantum field theories. And the topic of my talk is really how these techniques may be put at use for the phenomenology of heavy ion collisions. Now, I shall do this by starting from experimental facts and discussing how we try to understand these experimental facts in QCD-based models. This will lead me to open questions, and for these open questions I will seek some answers in strings theory. And then we face what is possibly the most difficult question at all, namely to discuss to what extent these answers have something to do with the questions we asked originally. So let me start by introducing you to the notion of jet quenching. Experimentally, what we observe is the suppression of single inclusive hadron spectra in nucleus-nucleus collisions. So if I look at a high PT single inclusive spectra, say of pions, then I know that this is the leading fragment of a parton, of a quark, say. And if I embed this process in a dense medium, then I know that there is an additional source of energy loss which may degrade the energy of this leading hadron. Experimentally, I characterize this medium-induced suppression by the nuclear modification factor, which just compares the yield observed in nucleus-nucleus collisions to the yield I would obtain in an equivalent number of nucleon-nucleon collisions. So this quantity is normalized such that it's 1 in the case of no suppression, and it's smaller than 1 in the case of suppression. Now, experimentally, I can study this pattern as a function of in-medium path length by varying the centrality of the collision. And what I observe is that for the most peripheral events, my nuclear modification factor is comparable with unity. However, as I increase the in-medium path length, as I increase the centrality of my collision, my rate drops dramatically. And for the most central collisions, I look at a factor 5 suppression out to the highest transverse momenta studied, 20 GeV. This is not the only experimental evidence we have that matter is extremely opaque in these collisions for the propagation of hard partons. Another example are high PT triggered hadron correlations. What I do is I trigger on a high PT particle. I look at the azimuthal distribution of this particle in phi. What I see is a peak near the trigger particle. This is a jet-like correlation. What I see in proton-proton and deuterium gold is a peak in the opposite direction. That is the recoil for a triggered particle. However, if I go to a central heavy ion collision, I blank out the opposite side. My recoil is completely stuck in the matter. So how do we try to account for these strong energy loss effects in QCD-based models? Let me do this schematic. High energy scattering in QCD can be described by Eichner-Wilson lines. The idea is that if I move with a hadronic projectile composed of partons of color alpha I at transverse positions xi into a target, and my target appears Lorentz contracted to the high energy, then the impact parameters do not change during the interaction. The color, however, of each parton rotates due to the target color field, so my S matrix is written as a bunch of Wilson lines. In a concrete example, I have a bare quark, say, and its first stressed gluon. If I move with that through a nuclear target, my outgoing wave function is just each parton trailed by these Eichner-Wilson lines of the target field in the corresponding representation. If I ask how many gluons are produced in such a process, then I have to look at the part of the wave function which is orthogonal to the incoming one, and I just count the number of gluons in this wave function. And in this schematic calculation, what I obtain is a radiation process which is essentially perturbative and which has one non-perturbative input. The input contains all the information about the target. This input is written as a target average of Eichner-Wilson lines, and it takes the form of a target expectation value of a light-like Wilson loop whose short distance dependence matters in what follows. Now, reality is more complicated. In particular, medium-induced radiation interferes with the standard D-club vacuum radiation of the quark. However, also in these more refined approaches, the only target information entering in these calculations is an expectation value of a light-like Wilson loop and its short distance behavior, the short distance behavior in the transverse direction being characterized by the BDMPS transport coefficient times a quadratic dependence. Now, people have tried to estimate this quenching parameter with crude methods which I cannot go into detail here. What matters is that this parameter can be thought of as describing the amount of transverse momentum squared transferred to the projectile per unit path length. And what I want to point out is that if you estimate the value of that by assuming a thermal target with a temperature of 300 MeV, you end up with estimates of the order of 1 GeV squared per Fermi. So the question which arises here is, can one arrive at more rigorous calculations, and how do such calculations look like if one does not base them on a perturbative idea? This question becomes more important if one looks at the comparison to phenomenology. There one observes that the parameter required to account for the suppression at RIC is at least a factor 5 larger than the parameter obtained from these estimates. And at least at that stage, there is now a qualitative question which arises and which is of importance for a quantitative understanding of heavy ion physics. The qualitative question here is whether such a large value can at all arise from a medium which presents a single momentum scale, a momentum scale of a few hundred MeV. So before I go further, I open here parenthesis to remark that, or to recall that if I look at a Wilson loop oriented in a time-like direction, a fundamental Wilson loop, then this target expectation value of this loop provides a working definition of a static quark-antiquark potential, and such free QQ bar energies have been studied extensively not only in string theory but also in lattice QCD at finite temperature, where one observes the melting, or an indication of the melting of quarkonia bound states. This is regarded as one of the major signals for the onset of a deconfinement phase transition. The technical remark I have here is that in a Minkowski space formulation, while this expectation value is the exponent of an imaginary quantity, the quenching parameter I introduced is an absorption parameter. It is the exponent of a real quantity. And we will see the consequences of that in a moment. So this closes this remark, and I come now to ADS-CFT. In heavy ion physics, many interesting questions involve small momentum transfers. Momentum transfers of the order of temperature 300 MeV, say. Accordingly, the coupling constant is large. Accordingly, perturbation theory becomes often unreliable. This is not only so for the quenching parameter and quark-conium dissociation I introduced here, but also for transport properties like shear viscosity. So at least at face value, a strong coupling expansion, which expands in 1/2th coupling, is very valuable to gain an understanding. One may remark that lattice QCD provides such a strong coupling calculation inside QCD. However, it's not particularly well suited for many problems of interest. For instance, if you look at these transport properties, you consider in the Green-Kubo formula a hydrodynamic limit of long wavelength, and that is very difficult to obtain if in an analytically continuation your smallest Matsubara frequency is 2 pi t. Also, as soon as you look at real-time dynamics, say the motion of a QQ bar pair or this Wilson loop along a light-like direction, clearly an imaginary time formalism is not suited. And this is just to say that ADS-CFT provides a natural framework to discuss these questions, thus providing us with a complementary insight, though not directly in QCD. Now, for this community, I certainly don't have to recall the content of the ADS-CFT correspondence. Let me just say that at present I focus on what is be called the simplest example, namely n equals 4 super Young-Mills theory, and that I work in the thermal sector where the gravity dual is given by an ADS5 Schwarzschild black hole matrix. So the prescription to calculate thermal expectation values of Wilson loops is then to determine the area of the world sheet which hangs down from the brain along the contour defined by this Wilson loop. And this area is defined by the Nambu-Goto action. So what enters here at the moment, we put our world, this brain, at a position lambda, which is not yet put to infinity, but will be put to infinity finally. What we have done in this way, we provide a standard parameterization of this world sheet, a two-dimensional parameterization, and what we do, we account for arbitrary orientations of this Wilson loop between time-like and light-like direction by boosting the ADS5 metric. So the metric has now a boost. It depends on eta, and eta is related to the velocity with which our metric moves with respect to the frame in which we write the Wilson loop. And then we define in a standard way boundary conditions. So what we have is we have a Wilson loop which is very long in a time-like or light-like direction, and which has a small transverse distance behavior we'll be interested in. And our boost parameter eta tells us about the orientation of that Wilson loop. Now we can, in our calculation, find two qualitatively different regimes. Either we keep eta, the rapidity, and hence the velocity of our QQ bar fixed, and then move our brain to infinity. In this case, we calculate the static QQ bar potential in a situation in which it sees a thermal wind sweeping over, so not in the thermal rest frame. And that, for this situation, we find that the worldsheet we observe is time-like, so the target expectation value is the exponent of an imaginary quantity, and that regime is square root cosh eta, so a measure of the velocity smaller than lambda. On the opposite side, we specify our light-like Wilson loop by first putting our loop to a light-like direction and then taking lambda to infinity. In this case, we recover a space-like worldsheet, and the short distance behavior of the Nambu-Goto action then gives access to the quenching parameter. Now, the result we obtain for this quenching parameter in this ordered limit is shown here. It's an explicit expression. For dimensional reasons, it's going with t cubed. It has a large prefactor. And now, before proceeding, I would like to do some numerology with this result. So what we have done is we have not calculated Parton energy loss in n equals 4 super-Young mills. We have calculated Parton energy loss in QCD perturbatively. We have found that it depends on one non-perturbative quantity, the quenching parameter, and we have calculated this quenching parameter in n equals 4 super-Young mills. And here's the result. If, and that turns out to be a big if we relate this result to QCD by fixing NC and alpha, the strong coupling constant, then we find that Q hat is of the order of 5 GeV squared per Fermi for a temperature of 300 MeV, and it is of the order of 10.6 GeV squared per Fermi for a temperature of 400 MeV. So we have a answer to our qualitative question whether such a large value can at all arise in a medium which presents only a scale of 300 MeV. Also, interestingly, this value comes close to experimental fits. But given that these methods do not have a particular track record of phenomenological success, the question is, of course, whether such a comparison is at all meaningful. Now, if I look at the structure of n equals 4 super-Young mills, I see that it is conformal. It has no asymptotic freedom, no confinement. It is maximally supersymmetric. It has no chiral condensate, and its particle content is very different from the particle content of QCD. So clearly the physics near the vacuum and the physics at very high energy can be expected to be rather different from the physics of QCD. If I look, however, at that situation at finite temperature, the situation looks slightly different. Yes, the theory is conformal. However, we have evidence from the lattice that at a few times Tc, lattice results are close to conformal. For instance, the velocity of sound is close to that expected from a conformal theory, and so on. Yes, the theory does not have asymptotic freedom and no confinement. However, neither of these are intrinsic properties of the quark-gluon plasma in QCD above the critical phase transition. Clearly, the theory is supersymmetric, but supersymmetry is badly broken at finite temperature. The theory doesn't have a chiral condensate, but the chiral condensate melts at the phase transition. The particle content is very different, but one wonders to what extent this may be taken into account by a proper normalization. So what I want to allude to here is an idea common to solid-state physics, that different matters can have very different microscopic physics, and yet they share generic features. For instance, all metals share generic features if I look at macroscopic properties. And one wonders whether there are universal, not in a mathematical sense at the moment, I cannot specify that, whether there are generic features of the large class of non-abelian thermal quantum field theories which all these theories have in common, and which would make us then more confident to apply to the conclusions to QCD. So that prompts us to explore the systematics beyond n equals 4 super Young-Mills. And one observation one makes in this context for the quenching parameter is that if we look at the entire class of theories with a supergravity dual, we see that these quenching parameters are related to each other by the square root of their central charges. So we have an idea of how they scale with a number of degrees of freedom. They scale weakly, but they scale. So this would, for instance, for QCD compared to n equals 4 super Young-Mills, be a correction factor of the order of 0.6 or so. Then there are theories, cascading theories, where one has investigated in this context minor deviations from conformality. One has an idea how this evolves. In principle, one would be very interested in finite coupling and NC corrections, though this turns out to be very hard and only partial results are known. In principle, one would like to know how these quantities change with chemical potentials. Now, let me step one step back. I mentioned that the quenching parameter is a description only of one quantity from n equals 4 super Young-Mills, not the entire Parton energy loss mechanism. Other groups have been more ambitious. They have modeled the entire process of Parton energy loss in n equals 4 super Young-Mills by taking a fundamental quark and dragging it through the medium. What one observes in this case is a very different physical mechanism. Namely, one excites essentially sound waves in the plasma which transport this energy away. Why? Because n equals 4 super Young-Mills is strongly coupled on all scales, not only on the scales of small momentum transfer. Also, the parametric dependence of the energy loss with energy is very different from the parametric dependence in QCD. It's proportional to energy. If one asks about the range of validity of this picture, a simple estimate can be based on the Schwinger mechanism, so you estimate from one in-field action at what scale this string, which is needed to track your particle, at which scale this force would create pair creation, and you see that you have to stay on the other side of the divider, which we used to calculate the quenching parameter. Let me finally, in the last 3 minutes, come to the case of space-like solutions of these Wilson loops, and which define confinement. So if one asks whether a QQ bar bound state survives in a thermal medium, one finds that below a screening length, the force binds this pair together. That is the string configuration. Above this length, the force is screened. Our calculation allows now to look at the velocity dependence of that quantity. We find that the screening length scales with the square root of the gamma boost factor, and this suggests that the dissociation temperature for bound states drops as our pair has finite velocity. So a pair which is moving through the thermal mint is more ready to dissociate than one it's at rest. And there is a quite significant phenomenology evolving around these ideas. There are numerous ways to continue these studies. One is to ask whether, and that leads possibly already to the next speaker, whether such findings can be supported in more realistic mesons. So, in particular, whether this velocity scaling of the dissociation temperature persists for realistic mesons. At the moment, we have work in progress to discuss this by introducing heavy fundamental quarks by D7 branes and studying then excitations of these D7 branes, mesonic excitations of these D7 branes, which would dissociate above some temperature. And what we study is the dispersion relation if we start moving these mesons. And we have preliminary results that we can confirm this velocity scaling in this refined setting. So let me finally thank my collaborators on that work, and let me point out that this is only the end of this talk. I have tried to stay focused to show something rather than to give a review, but it's clear that many other topics have been discussed in comparing ADS-CFT and QCD. I hope I've made it clear that a comparison and a phenomenological use is neither straightforward nor obviously far-fetched, and I expect that many further chapters will be written in the near future. Thank you very much.
Okay, are there any questions? Remarks, comments? Yes.
Hi. You mentioned that the definition of a jet quenching parameter at strong coupling was a working definition. I was wondering if you have a way of relating this particular coefficient, this Wilson loop, to the energy loss of the quark moving, or probe, heavy probe moving through some strongly coupled plasma.
So I use the word working definition solely in the context of the QQ bar static potential. There is a technical issue whether this loop, Wilson loop allows to define for you a static quark-antiquark potential at finite temperature. At zero temperature, it's the Wilson description. At finite temperature, there are subtleties which I cannot go into here related to Wick's theorem at finite temperature. So you ask whether you can turn a fermionic operator into such a Wilson loop, and that turns out to be subtle. That's also why it's important at the end to confirm such results with more refined descriptions of mesons. So that's concerning the word working definition. Concerning your question about quenching parameter, the quenching parameter itself, in the way used here, is used phenomenologically to account for the suppression of heavy quarks. The reason why this is so is that even in the presence of a mass, your Eichner formalism looks at the leading energy dependence, and the leading energy dependence is independence in which, in some aspects, you drop terms of mass over energy. So in short, if I look at a 10 GeV charm, I have a formulation exists which is written in terms of the quenching parameter, but which has the characteristic dead cone effect for a massive quark built in. What is really different between the drag solution and this quenching parameter is not so much mass versus not mass. What is different is that you have start from a picture of energy loss in which all aspects of your calculation are strongly coupled. That means your energy is radiated away in terms of sound waves, while in the QCD-based calculations, the gluon radiation of a massive quark is still a radiation of gluons, of particles, which then propagate with some multiple scattering. So physically, I find it very interesting that one has these two very different extreme descriptions at hand, because in some intermediate transverse momentum regime, experimentalists may have discovered some first indications for such sound waves. And if that turns out to be true, that would highlight much more the importance to play in between these two schemes.
Okay, any other questions? One more question.
You said that the device screening length is somehow related to this semi-classical shape of a worldsheet. But it was recently pointed out that where the device screening mass should be defined by long-distance correlation of Wilson loops at least.
So this Debye screening length appears in the perturbative estimates, which I showed. It's not directly related to the Wilson loop I have calculated here. There are numerous technical remarks one can make. One important thing which I have as a backup slide, and I will put it on the server, is to convince yourself that this is really a Wilson loop which you obtain from these target averages, and not a Schwinger-Keldysh contour which is used for the latter calculation. And you can show this explicitly in this formula.
Okay, if there are no further questions, let's thank the speaker again.